You know by this point in the book that I really like random matrices. They're fun and easy to work with. They can be great for education, for learning about linear algebra. So it's important to know how to create random matrices with lots of different kinds of properties that you might be interested in studying. For example, you already know how to create a random numbers matrix of any size and with any arbitrary rank, assuming that that rank is still consistent with the rules of rank. Okay, and that leads us to exercise 6 here. The goal of exercise 6 is to create symmetric matrices that have any eigenvalues that you specify. So you get to say what are the eigenvalues of this matrix, and you can also guarantee that this matrix will be symmetric. Okay, and so here is the algorithm to do this. Let's see. So you start with positive numbers on a diagonal matrix. So these are the eigenvalues. And here I'm just giving examples of numbers 1, 2, 3, 4 as eigenvalues. But I'll use random numbers actually when I show you the code. And then you want to create an eigenvectors matrix. Now, the thing to keep in mind is that the matrix of eigenvectors is a Q matrix. It's an orthogonal matrix. So you can craft random eigenvectors for a symmetric matrix from QR decomposition of a random numbers matrix. Okay, so lots of randomness all over the place. We're coming up with random numbers for the eigenvalues, random numbers for the eigenvectors, and then we are going to create a random numbers matrix. It's going to be symmetric, and then it's going to have the eigen values that we specified. Okay, so write all of that code out and then confirm that the assembled matrix is symmetric and its eigenvalues match the eigenvalues that you initially specified. So here are the 4 random eigenvalues. They are positive, and I multiply them by 5 for no particular reason, just to scale them up, because here they will be scaled between 0 and 1. So I don't know, I just wanted some larger eigenvalues. Here is our lambda matrix. You can see this is a vector, and then I push it through the diag function, which gives us out a diagonal matrix. Here I take the Q from QR decomposition of random numbers matrices. And now, for eigenvectors, we don't have this constraint that they need to be positive values. They can be positive or negative. And here you can see this is the diagonalization of a matrix, except we're doing it backwards, right? Normally, you start with this matrix A. This might be a data matrix, a transformation matrix, and then you implement eigendecomposition to compute these matrices. Here, we start by creating these matrices to have the properties that we want them to have, and then multiply them to produce a matrix. Okay, so then this code here will show you that the matrix is indeed symmetric because the matrix minus its transpose gives us a zeros matrix. And here, we need a drum roll. If you like, you can do a little drum roll on your desk, but not if you're in a library, because you have to be respectful of the people around you and so on. So here I am taking, just extracting these random numbers that I created in this lambda matrix and the eigenvalues of A, and I'm sorting them both. And amazingly enough, they're exactly the same. So I think that is super duper interesting. We just created a random numbers matrix. Let's have a look at this matrix here. Totally random numbers, unpredictable what these numbers are going to be, but we do know that they will have exactly the eigenvalues that we have specified up here.